Good morning, learners and viewers. Welcome to the session of Business and Masters of Business Administration. Today we will be talking about operations research, that is MMPO 001. We'll start with the background, or rather we can say that an overview of operations research. What operations research is, how it started, what are its applications. Operation research is a distinct discipline in its own way, but also become an important tool in all areas of study. Operation research as a formal subject is about 70 years old, and its origin may be traced to the later half of the World War II. It is an interdisciplinary approach that provided useful solutions to problem of military operations in World War II and has since been equally found successful in non-military operations too. Most of the OR techniques that are commonly used today were developed over approximately the first 20 years following its inception. The tools of operation research are not from any one discipline, rather, mathematics, statistics, economics, engineering, psychology, etc., have contributed to this newer discipline of knowledge. Operation research takes tools from subjects like mathematics, statistics, economics, engineering, psychology, etc., and combines them to make a new body of knowledge for decision making. Today, it has become a professional discipline that deals with the application of scientific methods for decision making and especially to the allocation of scarce resources. OR worker tries to find out order in apparent chaos by identifying the structure in complex situations. He develops the understanding of how the components of organizations interact so as to explain and predict the effects of action taken on these components. Much of this work is done with the help of analytical and numerical techniques and by developing and manipulating mathematical and computer models of organizational systems. Such systems may be composed of people, machine, and procedures. Complete information about such a system may not be available. A purpose of OR is to provide a rational basis for making decisions in the absence of complete informations. Operations research can also be treated as science devoted to describing, understanding, and predicting the behaviors of systems, particularly man machine systems. Thus, operation research workers are engaged in three classical aspects of science. First one, describing the behavior of systems. Second one, analyzing this behavior by constructing appropriate models. And third one is using these models to predict future behavior, that is, the effect that will be produced by changes in the system or in the methods of operation. Operation research function is a staff function. Operation research is assistance to executive in improving the operations under their control. What particularly distinguishes operation research from other research and engineering is its emphasis on analysis of operation as a whole. It is an interdisciplinary approach that provides useful solution to problems of military operations in World War II and has since been found equally successful in non-military operations too. Most present-day business applications are primarily concerned with mathematical and statistical analysis of the results of possible alternatives. Actually, often using techniques specially designed or refined for business problems, operations researchers have been able to provide remarkable and diverse benefits to the companies. Some such benefits are improved inventory and reorder policies, minimum cost production schedules, optimum location and size of warehouses, and guidance in sales and advertising policies. The basic pattern applied in clarification of various courses of action, open estimation of the outcome to be expected from each, and evaluation of these in terms of the overall goal desired. Now, we move to what is the history of this operation basis, how it started, when it started, and how it was thought for. OR had its beginning in World War II. The term operations research was coined by McCloskey and Tufting in 1940 in UK. British scientists set up the first field installation of radars during the battle and observed air operations. Their analysis of these led to suggestions that greatly improved and increased the effectiveness of British fighters and contributed to successful British defense. Operation research was then extended to anti-submarine warfare and to all phases of military, naval, and air operations, both in Britain and the United States, and was incorporated in the post-war military establishments of both the countries. The effectiveness of operation research in military spread interest in it to other governmental departments and industry. In USA, the National Research Council formed a committee on operation research in 1951, and the first book on the subject, Methods of Operation Research, by Morse and Kimball, was published. In 1952, the Operation Research Society of America came into being. Success of OR in military attracted the attention of industrial managers who were seeking solutions to their complex problems. Today, almost every large organization or corporation in affluent nations has staff applying operations research, and in government, the use of operation research has spread from military to widely varied departments at all levels. This general acceptance of OR has become as managers have learned the advantage of scientific approach on which OR is based. Availability of faster and flexible computing facilities and the number of qualified OR professionals enhanced the acceptance and popularity of the subject. India was one of the first few countries who started using OR. In 1949, first OR unit was established in Regional Research Laboratory at Hyderabad. At about the same time, another group was set up in Defense Science Laboratory to solve the problems of stores, purchase, and planning. In 1953, OR unit was established in Indian Statistical Institute, Calcutta, with the aim of using OR methods in national planning and survey. OR Society of India was formed in 1955. The society is one of the first members of International Federation of Operation Research Societies. The society started publication OpSearch, a learned journal on the subject in 1963. Today, OR is a popular subject in management institutes and schools of mathematics and is gaining currency in industrial establishments. What are the approaches, techniques, and tools which are used in operation research? And OR team, in some companies, this may be a single individual, consists of trained researchers utilizing the skills and tools of applicable science without any preconceived idea of what the correct solution should be. The first step is to formulate the problem, after which a mathematical model is generally constructed to represent the system being studied. Mathematical model or conceptual model may be in the form of an equation or formula developed to relate important factors or the variables of the operations under study. The model then can be tested and operated upon mathematically to determine the effects of changing the values of the variable. Optimization of some criteria may be the purpose of such an exercise. What is meant by optimization? Optimization means achieving the best, maximum, or minimum value of the criteria. Sub-optimization occurs either when some criteria subordinate to the overall criteria is optimized or when the overall criteria is optimized over only a portion of the total of all possible alternative actions. A criteria is a measure by which the results can be evaluated. It means it measures the effectiveness of the operations under study in terms of the ultimate objectives of the operations and maybe net profit, return on investment, that is what we call it as ROI, cost, or some other thing appropriate to a particular study. Operation research uses any suitable technique or tools available. These frequently include common mathematical or statistical procedures, cost analysis, or electronic computation. However, OR analysts have given special emphasis to the development and use of the techniques like linear program, waiting line theory, game theory, inventory control models, and simulation. In addition, some other common tools are non-linear programming, integer programming, dynamic programming, sequencing theory, Markov process, network scheduling, what we call it as BERT and CPM, symbolic logic, information theory, and utility value theory. We will be discussing initially what they actually mean, and later we will be solving the problems. Brief explanation of these is as we will start with linear programming. Linear programming is basically a constraint optimization technique which tries to optimize some criteria within some constraints. It consists of an objective function, which is some measure of effectiveness like profit, loss, or return on investment, and several boundary conditions putting restriction to the use of the resources. Objective function and boundary conditions are linear in nature. There are methods available to solve a linear programming problem. Second one is non-linear programming. Non-linear programming methods may be used when either the objective function or some of the constraints are not linear in nature. Non-linearity may be introduced by such factors as discount on price of purchase of large quantities and graduated income tax, etc. Linear relationships may be employed to approximate non-linear conditions, but the approximation becomes poorer as the range is extended. Non-linear methods may be used to determine the approximate area in which a solution lies, and linear methods may then be used to obtain a more exact solution. Next comes integer programming. Integer programming method may be used when one or more of the variables can take only integral values. Examples are the number of trucks in a fleet, the number of generators in a powerhouse, and so on. Approximate solution may be obtained without using integer programming methods, but the approximation generally becomes poorer as the number becomes smaller. There are techniques to obtain solution of integer programming problems. Fourth one is dynamic programming. Dynamic programming is a method of analyzing multi-stage decision processes in which each elementary decision is dependent upon those preceding it as well as upon external factors. It drastically reduces the computation efforts otherwise necessary to analyze results of all possible combinations of elementary decisions. Fifth one is waiting line theory or queuing theory. Waiting line theory or queuing theory deals with the situation in which queue is formed. Customers waiting for service, machines waiting for repairmen, and aircraft waiting for landing strips are some of the situations in which queue is formed. If we assume that there are costs associated with waiting in line, and if there are costs of adding more channels, that means facilities, we want to minimize the sum of costs of waiting and the cost of providing service facilities. Waiting line theory helps to make calculations like expected number of people in the queue, expected waiting time in the queue, expected ideal time for the servers, etc. These calculations then can be used to determine the desirable number of service facilities. Sixth one is game theory. Game theory is used for decision making under conflicting situations where there are one or more opponents. Opponents in game theory are called players. The motives of the players are decoptimized. The success of one player tends to be at the cost of others, and hence they are in conflict. Game theory models a conflict situation and helps us to improve the decision process by formulating appropriate strategy. Next one is inventory control models. When to buy, how much to buy, and how much to keep in stores are some of the questions which production managers, purchase managers, and material managers addresses themselves to. Inventory control models provide rational answer to these questions in different situations of supply and demand for different kind of materials. Inventory control models helps managers to decide reordering time, reordering level, and optimal ordering quantity. The approach is to prepare a mathematical model of the situation that expresses total inventory cost in terms of demand, size of order, possible over or understocking, and other relevant factors, and then to determine optimum order size, optimum order level, etc., using calculus or some other technique which is available. Simulation. It is basically data generation technique. Sometimes it is very risky, cumbersome, or time consuming to conduct real study or experiment to know more about a situation or problem. Analytical methods also cannot be used in all the cases. Sometimes, due to large number of variables or large number of interrelationships among the variables and the complexity of the relationship, it is not possible to develop an analytical model representing the situation. Sequencing theory or sequencing technique. It is related to waiting line theory. It is applicable when the facilities are fixed, but the order of services may be controlled. The scheduling of services or the sequencing of job is done to minimize the relevant costs. Markov process. Markov process for decision making is used in situations where various states are defined. The probability of going from one state to another is known and it depends on the present state and is independent of how we have arrived at that state. Theory of Markov process help us to calculate long-run probability of being in a particular state, steady state probability. This steady state probability is used in decision making. Network scheduling, which includes PERT and CPM. Network scheduling is a technique used to plan, schedule, and monitor large projects. Such large projects are very common in the field of construction, maintenance, computer system installation, research and development, designs, etc. The technique aims at the minimizing trouble spots such as delay, interruptions, and production bottlenecks by identifying critical factors and coordinating various parts of overall job. The whole projector job is diagrammatically represented with the help of network made of arrows representing different activities and interrelationship among them. Such a representation is used for identifying critical activities and critical paths. Two basic techniques in network scheduling are program evaluation and review technique, that is, in short, we call it as PERT, and critical path method, what is CPM. CPM is used when time taken by activities in the project are known for sure, and PERT is used when activity time is not known for sure, only probabilistic estimates of time is available. Symbolic logic. Symbolic logic deals with substituting symbols for words, classes of things, or functional system. It incorporates rule, algebra of logic, and propositions. There have been only limited attempts to apply this technique to business problems. However, it has been extensive application in design of computing machine. Information theory. It is an analytical process transferred from the electrical communication field to operational research. It seems to evaluate the effectiveness of information flow within a given system. Despite its application mainly to communications network, it has an indirect influence in simulating the examination of business organizational structures with a view to improving information or communication flow. Then comes utility value theory. Utility value theory deals with assigning numerical significance to the worth of alternative choice. To date, this has been only a concept and is in the stage of elementary model formulation and experimentation. When developed, this may be very useful in the decision making process in assessing the world of various possible outcomes. What are the phases and processes of OR study? OR is a logical and systematic approach to provide a rational basis for decision making. The phases and processes of OR study must also be quite logical and systematic. There are six important steps in OR study, but it is not necessary that in all the studies, each and every step is invariably present. These steps are arranged in the following logical order. Step 1. Observe the problem environment. It is a process of OR study in which observing the problem environment is. The activities that constitute these steps are visits, conferences, observations, research, etc. With the help of such activities, the OR scientists get sufficient information and support to proceed and is better understanding the problem. In this step, not only the problem is defined, but also uses objectives and limitation of the study are stressed in the light of the problem. The end results of this step are clear grasp of need for a solution and understanding of its nature. Step 3 is to develop a model. A model is representation of some real or abstract situation. OR models are basically mathematical models representing systems, processes, or environment in the form of equations, relationships, or formulae. The activities in this step defining interrelationship among variables, formulating equations using known OR models, or searching suitable alternative models. The proposed model may be field tested and modified in order to work under stated environment constraints. A model may also be modified if the management is not satisfied with the answer that it gives. Step 4 is select appropriate data input. Garbage in and garbage out is a famous saying. No model will work appropriately if data input is not appropriate. Hence, tapping right kind of data is a vital step in OR process. Important activities in this step are analyzing internal external data and facts, collecting opinions and using computer data banks. The purpose of this step is to have sufficient input to operate and test the model. Step 5 is to provide a solution and test reasonableness. It is a step which is to get a solution with the help of model and data input. Such a solution is not implemented immediately. First, the solution is used to test the model and to find limitations, if any. And if the solution is not reasonable or if the model is not behaving properly, updating and modification of the model is considered at this stage. The end result of this stage is solution that is desirable and supports current organizational objectives. Step 6 is the implementation of the solution. Implementation of the solution obtained in previous step is the last step of OR process. In OR, the decision making is scientific, but implementation of decision involves so many behavioral issues. Therefore, the implementing authority has to resolve the behavioral issues. He has to sell the idea of use of OR not only to the workers but also to the superiors. Distance between management and OR scientists may offer a lot of resistance. The gap between one who provides a solution and one who wishes to use it should be eliminated. To achieve this, OR scientists as well as management should play a positive role. What are the limitations of operational research? Operation research has certain limitations. However, these limitations are mostly related to the problems of model building and the time and money factors involved in its application rather than its practical utility. Some of them are magnitude of computations. OR tries to find out optimal solution taking into account all the factors. In the modern society, these factors are enormous and expressing them in quantity and establishing relationships among these require voluminous calculations which can only be handled by machines. Non-quantifiable factors. OR provides solutions only when all the elements related to a problem can be quantified. All relevant variables do not lend themselves to quantification. Factors which cannot be quantified find no place in OR models. In OR, do not take into account qualitative factors or emotional factors which may be quite important. Distance between manager and operation researchers. OR being specialized job requires a mathematician or a statistician who might not be aware of the business problems. Similarly, a manager fails to understand the complex working of OR. Thus, there is a gap between the two. Management itself may offer a lot of resistance due to conventional thinking, money, and time cost. When the basic data are subjected to frequent changes, incorporating them into the OR models is a costly affair. Moreover, a fairly good solution at present may be more desirable than a perfect OR solution available after some time. Implementation. Implementation of decisions is a delicate task. It must take into account the complexities of human relations and behaviors. Sometimes this resistance is offered only due to psychological factors. What is the relationship between OR specialist and manager? The role of OR specialist is to help the manager make better decisions. Decision making is a key responsibility of managers. Managers now need and in the future will need OR specialists because the size of organizations is increasing to the point where they are becoming unmanageable for traditional means and methods. Even without this problem, managers face enormously complicated and fast changing situations. Creative and workable solutions to these problems require the cooperative involvement of OR specialists and managers. Decision makers move towards OR approach when they see the problem as complex, involving many variables and relationships. They don't think they can develop a solution without OR methods. They view the problem as repetitive. Thus, quantitative solutions, which is repeated, will save the time and money. They initially feel that the data in the problems are numeric. They know of similar situations in which decisions have been improved by using OR techniques. Skills in qualitative analysis are inherent in the manager and generally increases with experience. Skills in quantitative analysis can be acquired by the study of mathematical tools such as those discussed above. Using these tools, manager can improve their decision-making effectiveness. They can compare and combine the qualitative and quantitative information at their disposal and thus make the best possible decisions. Now we will talk about typical applications of operation research. Now we will see how, in which areas ORS being used or can be used. We talk about accounting that is related to finance. It is used in cash flow planning, credit policy analysis, planning of delinquent account strategy. And if we talk about construction, allocation of resources to project, we have already said that there is PERT and CPM tech methods which are used for construction work. Determination of proper workforce, deployment of workforce, project scheduling, monitoring and control. Finance, dividend policy making, investment analysis, portfolio analysis. In manufacturing, inventory control, projection, marketing balance, production scheduling, production smoothing. Organization behavior, personal justification of planning, scheduling of training programs, skill balancing. In purchase, material transfer, optimal buying, optimal reordering, and research and development, control of R&D projects, product introduction planning. Now we talk about OR in the real world. Here are some of the examples of successful real-world application of operations research. These provides an appreciation for the diverse kind of problems that OR can address, as well as for the magnitude of the savings that are possible. Without any doubt, The best source of case studies and details of successful applications is the Journal Interfaces, which is a publication of Institute for Operation Research and Management Sciences. In short, we call it as INFOS. This journal is oriented towards the practitioner, and much of this exposition is in layperson's term. At the same point, every practicing industrial engineer should refer to this journal to appreciate the contribution that OR can make. All of the applications that follow have been extracted from recent issues of interfaces. Some examples of successful OR projects are, we start with production planning at Harris Corporation. It is a in its semiconductor section. For our first application, we look at the area that is readily appreciated by every industrial engineer, that is production planning and due date quotation. The semiconductor section of Harris Corporation was, for a number of years, a fairly small business catering to a niche market in the aerospace and defense industries, where the competition was minimal. However, in 1988, a strategic decision was made to acquire General Electric semiconductor product lines and manufacturing facilities. This immediately increased the size of Harris Semiconductor operations and product lines by roughly three times, and more importantly, capitulated Harris into a commercial market areas such as automobiles and telecommunications, where the competition was stiff. Given the new diversity of product lines and tremendous increase in the complexity of production planning, Harris was having a hard time meeting delivery schedules and in staying competitive from a financial perspective. Clearly, a better system was required. Second case is gasoline blending at Texaco for another application to production planning, but this time in a continuous or opposed to discrete production environment. We look at a system in use at Texaco. One of the major applications of OR is in the area of gasoline blending at petroleum refineries, and virtually all major oil companies use sophisticated optimizing models in this area. At Texaco, the system is called StarBlend and runs on networked microcomputers. As some background, the distillation of crude petroleum product produces a number of different products at different distillation temperatures. Each of these may be further refined through cracking, where complex hydrocarbons are broken into simpler ones, and recombination. These various output streams are then blended together to form end products such as different grades of gasoline, leaded, unleaded, super unleaded, etc., jet fuel, diesel, and heating oil. The planning problem is very complex since different grades of crude yield different concentrations of output streams and incur different costs. And since different end product fetches different revenues and use different amounts of refinery resources, we can see that how much complex the problem is. Third one is fleet assignment at Delta Airlines. One of the most challenging as well as rewarding application area of OR has been the airline industry. We briefly describe here some application of Delta Airlines. The problem solved is often referred to as the fleet assignment problem. We will be discussing this in assignment computation when we will be doing it. Delta flies over 2,500 domestic flight legs each day and uses about 450 aircrafts from 10 different fleets. And the objective was to assign aircraft to flight legs in such a way that revenue from seats are maximized. The trade off is quite simple. If a plane is too small, then the air loses potential revenue from passengers who cannot be accommodated on board. And if it is too large, then the unoccupied seats present lost revenue. In addition to the fact that larger aircraft are also more expensive to operate. Thus, the objective is to ensure that an aircraft of the correct size be available when required and when where required. Unfortunately, ensuring that can happen is tremendously complicated since there are a number of logistical issues that constrain the availability of aircraft at different times and at different locations. Fourth one is Key Corp Service Excellence Management System. For our final application, we turn to the service sector and an industry that employs many industry engineers, banking. This application demonstrates how operation research was used to enhance productivity and quality services at KeyCorp, a bank holding company headquartered at Cleveland, Ohio. Faced with increasing competition from non-traditional sources and rapid consolidation within the banking industry. KeyCorp aim was to provide a suite of world-class financial products and services as opposed to being a traditional bank. The key element in being able to do this effectively is high quality customer service. And a natural trade-off faced by a manager was in terms of staffing and service. Better service in the form of shorter wait timing required additional staffing, which come at higher cost. The objective of the project was to provide managers with complete decision support system, which was dubbed SEAMS, that is Service Excellence Management System. Now, we move to Unit 2, which is linear programming. Here, we will be talking about graphical method. We have an introduction to the linear programming, what linear programming is. Now we will see how it is applied actually to a problem. Linear programming is a special and versatile technique which can be applied to a variety of management problems, risk, advertising, distribution, investment, production, refinery, operations, and transportation analysis. The linear programming is useful not only in industry and business, but also in non-profit sectors such as education, government, hospital, and libraries. The linear programming method is applicable in problems characterized by the presence of decision variables. The objective function and the constraints can be expressed as linear functions of the decision variables. The decision variables represent quantities that are in some sense controllable inputs of the system being modeled. An objective function represents some principal objectives criteria or goals that measures the effectiveness of the system, such as maximizing profit or productivity or minimizing cost or consumption. There is always some practical limitation on the availability of the resources, such as man, material, machine, time for the system. These constraints are expressed as linear equations involving the decision making. Solving a linear program problem means determining actual values of the decision variable that optimize the objective function, subject to the limitation imposed by the constraints. The main important feature of linear programming model is the presence of linearity in the problem. The use of linear programming model arises in a wide variety of applications. Some model may not be strictly linear, but can be made linear by applying approximate mathematical transformations. Still, Some applications are not at all linear, but can be effectively approximated by linear models. What is the application of linear programming? Linear programming is a widely used technique of OR and in almost every decision of the business and management. However, linear programming is exclusively used in the following areas: production management, personal management, financial management, marketing management. How this formulation of linear programming problem is done? What is the method and how we will start it? The linear programming problem formulation is illustrated through a product mix problem. A product mix problem occurs in an industry where it is possible to manufacture a variety of products. A product has a certain margin of profit per unit and uses a common pool of limited resources. In this case, the linear programming technique identifies the product's combination which will maximize the profit subject to the availability of limited resource constraints. Now, we take up an example of linear programming, how this is used and how this is applied to the industry. Suppose an industry is manufacturing two types of product, P1 and P2. The profit per kg of two products are rupees 30 and rupees 40 respectively. These two products require processing in three types of machine. The following table shows the available machine hours per day and the time required on each machine to produce 1 kg of P1 and P2. Now the question is, formulate the problem in the form of linear programming model. Now, how this is transformed into a table. When we are talking about machine 1, the cost or the profit on product 1 is rupees 30 and on number 2 product is rupees 40. On the right column we can see that there are total number of machines asked per day. Machine 1 and machine 2 and machine 3. Three machines are being used for making up a product. Suppose we introduce the decision making variables x1 be the amount of P1 and x2 be the amount of P2. Now what we will be doing? We have to maximize it. In order to maximize the profit, what we are going to do? We are going to multiply 30 by x1 plus 40 x2. This is our objective function because this is what we are supposed to maximize. Now, what are the constraints to it? If we go back down to the table, here we can see that machine 1 is available for 600 hours per day and machine 2 for 800 and machine 3 for 1100. Now what to do? How this can be formulated? 3x1 plus 2x2. First of all, initially we will write equal to 600. Secondly, 3x1 plus 5x2 is equal to 800. And the third one is 5x1 plus 6x2 is equal to 1100. Now the thing is that if you go back to the problem, it clearly states that these machines are basically available for 600, 800 and 1100. In that case, we are going to use less than equal to sign. But this is the maximum limit from where these machines can be used per day. So that is why that equal to sign will be replaced by less than equal to. So in all, we can see that we have formed these equations. But x1 and x2 will always be greater than or equal to 0. They cannot be a negative production or they cannot be a negative number. That means this is a product mix problem in the linear programming model. And that statement, what was given to us, has been transformed into these conditions. We have to maximize 30x1 plus 40x2. What are the subject to the conditions? That is 3x1 plus 2x2 less than equal to 600. 3x1 plus 5x2 less than 800. And 5x1 plus 6x2 less than equal to 1100. And x1 and x2 both will be greater than or equal to 0. This is the basic procedure for formulating up an equation. We take up another example. Here we have to maximize the profit. A company produces two types of cowboy hats. Each hat of type 1 requires twice as much labor as the second type. The company can produce a total of 500 hats a day. The market limits the daily sales of first and second type to 150 and 250 hats. Assuming that the profit per head are rupees 8 per type of A and rupees 5 per type of B. You have to formulate the problem as linear programming model in order to determine the number of heads to be produced by each type so as to maximize the profit. Here two types of heads are being manufactured. So we can say that let type 1 be x1 and type 2 be x2. So we have to maximize it. Maximization process will be related to its cost. That means we can see that we have to maximize 8x1 plus 5x2. Later how this is transformed. Same if we talk about the labor time for the total production. It is 2x1 plus x2 less than equal to 500. And for number of heads of type A to be sold, that is x1 should be less than equal to 150. And x2 should be less than equal to 250. But the numbers of the heads will be x1 and x2 both greater than equal to 0 because numbers cannot be negative. That means that these are non-negativity constants. Now, this is a basic problem which consists of different type of constraints. A company owns two floor mills, A and B, which run different production capacities of high, medium, and low quality floor. The company has entered a contract to supply floor to a firm every month with at least 8, 12, and 24 quintals of high, medium, and low quality respectively. It costs the companies rupees 2000 and rupees 1500 per day to run mill A and B respectively. On a day, mill A produces 6 to 4 quintals of high, medium, low floor, and mill B produces 2, 4, 12 quintals of high, medium, and low floor respectively. How many days per month should each be operated in order to meet the contract order most economically? Now, this much, the information what has been given to us has to be transformed into the form of equations. Now, we will define x1 and x2 are the mills A and B. Initially, what we are going to do, we have two mills, mill A and mill B, and we have three types of floors, that is high, medium, and low. Here we can see that we are talking about the what are the resources to be calculated. We have resources in terms of quintals. Supply what is required for different levels of material. It is high, medium, and low. For high, it is 8. For medium, it is 12. And for low, it is 24. As far as the usage of mills are concerned for different products, this is tabulated in for 6 for high quality, 2 for medium quality, and 4 for low. And for mill B, 2 for high, 4 for medium, and 12 for low. After this, the second step is to convert this information into inequations. What we will be doing? We have to minimize 2000 x1 plus 1500 x2, subject to 6x1 plus 2x2 should be greater than equal to 8. 2x1 plus 4x2 should be greater than equal to 12. 4x1 plus 12x2 should be greater than equal to 24. And x1 and x2 both will be a non-negative number. That means they will be greater than or equal to 0. Now, after this, the next step will be converting this into a graphical representation. I'm just providing a brief of how these coordinates are formed and which quadrants are there. Your graph sheet will be like this. We have to draw quadrants along x and y. You can see over there your x coordinate, numbers in brackets, x is your x coordinate and y is in y coordinate. If we talk about the quadrant, we will be considering only first quadrant, because in that case only, in that region only, x will be greater than equal to 0, and the other one, the other information will be greater than or equal to 0. So we will be talking about quadrant 1 only. In quadrant 1, x and y both are positive. In quadrant 2, x is negative and y is positive. Quadrant 3, x and y both are negative. And in quadrant 4, x is positive and y is negative. Since we are talking about non-negative constraints, so we will be considering or we will be talking about the quadrant 1 area only. To draw or to first step initially, what we have found that the equations are in the form of ax plus by equal to 0, c. What you are going to supposed to do, first of all, divide both sides of these equation by c. So you will be getting ax by c plus by c equal to 1. Just drop that a from numerator to denominator. That will be x upon c by a plus y upon c by b equal to 1. This, or where c by a is equal to a and c by b is equal to b. This is basically an intercept form of equation. This conversion of linear equation into intercept form of equation reduces the time for solving the equation, and it facilitates a learner to draw this diagram quickly. You can see that A is marked over there, A comma 0, and B is on y-axis, that is 0 comma B. We have to convert, we have to use intercept form. That is the easiest method to solve the problems graphically. Two real expressions of real numbers related to the symbol are less than, greater than, less than, equal to, or greater than, equal to are called inequalities, and we will be using less than, equal to, or greater than, equal to in our problems. Graphical solution to inequalities with two variables. Solution to linear inequalities are a shaded half plane bounded by a solid line or dashed line. In our case, it will be a solid line because we will be using greater than, equal to sign or less than, equal to sign. This boundary is either included in the solution or not, depending on the given inequality. If we are given a strict inequalities, we use the dashed line to indicate that the boundary is not included. And if we are given an inclusive inequality, we use a solid line to indicate that it is included. That means that is only done when the case is less than equal to or greater than equal to. Now the problem is we have to find a solution, graphical solution to this y is equal to is greater than minus 3x plus 1. First of all, we will be converting this equation. We will be converting into an equation form. That means we will be removing that greater than sign. We will be making it as an equation. That equation will be y is equal to minus 3x plus 1. And we will be converting this equation into x by a plus y by y equal to 1 form. And here in this problem, x upon 1 by 3 plus y upon 1 equal to 1 is the equation of the conversion. And the point will be 1 by 3 comma 0 and 0 comma 1. You can see the green dot, and on y-axis that is 0 comma 1. And on x-axis is almost equal to 0.33 on the x-axis. So this is how a graphic, and since the sign is greater than, we have drawn it with a dotted line. If that would have been a greater than equal to, we have used it a solid line. We will be concluding today's session with this.